Now we're going to look at operations with radical expressions. So we're going to look at multiplying, dividing, adding, and subtracting these radical expressions, and then we're going to ask you to perform the indicated operation and simplify in simplified radical form. So you don't have to put it back into a rational exponent form. And so if I look at something like this, I have a radical multiplied to a radical. And so the rule is when they're the same index, we can actually multiply and put them underneath one radical and multiply them together. That's using our rules. And then my next step will be like bases, add your exponents. Now the simplified radical form is going to be divide your index into your power. It goes into it twice, and how many do you have left inside of the house? You leave it in the same house, it's got to have the same index. It goes into, and you have one remaining because 3 went into 7 twice, which is 3 times 2 is 6, and there's one remainder, so there's one left in the house, and that would be the only answer for simplified radical form. Now something like this, dividing two radical expressions. Use the rules to your advantage. Sometimes it's, you could simplify this, you could do both ways. You could simplify this first, simplify this next, and then try and simplify at the end. I actually look at this, I think I'm gonna combine it all into one fraction of a square root like that, and it might help me out. I like to flip-flop back and forth sometimes just to see if it's gonna make it easier. So I know separating them, I can write it as 1. Now I can use my exponent rules. 90 divided by 2 is 45. X to the 11 over x to the 4, 11 minus 4 is going to be x to the 7. Now I don't have a fraction. That's a little bit easier to do. Now, this is not a perfect square number, so I try and think of the largest factor that's a perfect square number of 45, and I believe it's 9, right? Because 9 times 5 is 45. And so, and you can remember this has an index of a 2. You can add it if you want to. And I should end up getting, this is the square root of 9 times 5, x to the 7th. You don't have to write that. If you can recognize it, you can actually jump to the answer, but I will put it up here. So I'll end up getting, I'm going to write this as the square root of really 3 squared times 5 times x to the 7th. You wouldn't actually have to show that either. If you know square root of 9 is 3, just take your 3 out. So I end up with 3 times the square root, I forgot about my variable. This index is a 2. 2 goes into 7 how many times? It goes in 3 times with one remainder. And then you're left with underneath the square root of 5 and 1x. And so that would be your final answer in simplified radical form. Now if we're looking at things like this, I have all constant radicands again. That's okay. Let's look at just simplifying each first, because I can't add or subtract things. They're not, like radicands have to, like radical expressions have to have the exact same index with the exact same radicand to be able to add or subtract them. So they're like apples with apples, just like we did with other stuff in algebra. You have to have the same radicand, the exact same index to be able to add or subtract them. Unlike when we were dealing with multiplication, the radicands can be different when you're multiplying, as long as the index is the same, so that you have the same index and stick underneath 1. Here, I can't subtract these yet, but I can try and simplify and see if anything will subtract. So this actually, if I recognize this is going to be 3 to the 3rd power minus, I recognize this to be 16 times 5, which is really 4 squared times 5. I'm trying to find the perfect square factor. That's the largest. You could just put 16 times 5, and you know there's square root's 4. And then this one is 25 times 3. So it's going to be 5 squared times 3. So breaking that down and getting to that process is important. I could also write this just 3 squared times 3, but I know my index goes into that, so I'm going to take 1 3 out. 1 still stays inside. This one I'm going to take a 4 out. I still have a 5 inside, and then this one, take a 5 out, and I still have a 3 inside. But now I'm asking you to simplify this. So I'm asking you to add or subtract these things. You have to have the same index with the same, they're all the same index, but have to have the same radicand also to be able to subtract or add these. So I have 3 roots of 3s, like 3 apples, plus 5 roots of 3s, plus 5 apples. I can actually combine those. These are different. These are like oranges or something different. So 3 plus 5, I end up with 8 of these roots of 3's, and I cannot combine the 4 root of 5, so that has to stay separate. It's all because of your order of operations. And I got a little close to that lower problem, so let's draw a line here so you can see the difference. Okay, so the last example, what if I'm multiplying and you have just these number radicands, and these are actually conjugates, right? They're binomial conjugates. They're same exact terms, middle sign, back signs are opposite. And so what that means, we've learned in the past in factoring and that kind of thing, the middle terms wipe out when you multiply these. But let's just do the distributive property. Distribute and then distribute. Combine your like terms. So you end up getting, what is the square root of 5 times the square root of 5? It's just 5. The reason being, square root of anything, say if I went off to the side, square root of 5 times square root of 5 is actually the square root of 5 squared, right? Or 5 times 5, which is the square root of 5 squared, which is just 5. So the square root of any number times the square root of the exact same number is going to get rid of the root symbol. So you just end up with a 5. Now square root of 5 times negative 3 is going to be minus 3 root of 5. Now distribute the positive 3 through, you get a plus 3 root of 5. So notice that this little like terms, opposite signs, the exact same amount of them, they'll wipe out. And then minus 9, you multiply your positive 3 and negative 3. So these are just going to wipe out. You end up with 5 minus 9, which is a negative 4. We're going to use this to our advantage when we do something called rationalizing the denominator in the next few problems.